All right, so week number 10 is on geometrical optics, and actually two chapters, geometrical optics and instruments, chapters 32 and 33. So the screencasts have two parts. Part one will be on theory, that's this part, and part two will be on applications, mirrors and lenses. Part one is on reflection and refraction and other properties of electromagnetic waves. So for this, you should look up anything you don't understand in chapter 32. Last week we studied electromagnetic waves in matter. No. This week we're studying electromagnetic waves in matter. So far, we have, in fact, only considered electromagnetic fields in empty space. That is to say, systems with fields E and B. Now, the space isn't completely empty because the fields fill up the space, but we have fields, we have charges, an isolated charge Q, or maybe a charge density rho of x and t. Currents could be just a moving charge, Q times V, where V is the velocity of the charge. Or it could be a current density, J, such as the current in a wire. Well, of course, there is matter present in the charges and the currents, but we haven't considered systems with ordinary matter. The one exception is when we talked about dielectrics and capacitors. So there is matter present, but it's just the matter that's necessary to supply charge or carry current. But what if there's some additional matter? Well, that will be the subject of the screencast today. And we'll eventually apply that to electromagnetic waves in matter. So here's an example of a problem that we did not consider. Two charges, an isolated charge plus Q and another one minus Q. This could be two charged spheres or something like that. And nearby, or in the same volume, a piece of glass. Okay, well, we didn't consider that problem. I mean, we might ask, what's the electric field inside the glass? For that matter, what's the electric field outside the glass? Is it just the same if the glass were not present? No, the glass affects the electric field. Glass is an insulator, so it doesn't carry any currents. However, the molecules of glass are polarizable. That is to say, the positive part of the molecule can be pulled apart from the negative part of the molecule. This is what we call a dielectric. A dielectric can be polarized, but it can't have current. So what will happen is a molecule inside the glass will be distorted by the electric field. There's got to be an electric field because there are charges present. So these charges will polarize the molecules in the glass. And the result will be there'll be some negative charge pulled up to the upper surface, which is closer to this positive charge. So it will be pulling negative charge upward, and the upper surface will become negatively charged. And, of course, the glass is electrically neutral, so if the upper surface has negative charge on it, then the lower surface has to have some positive charge. Now, this separation of charge does not occur because of current, because glass is an insulator. It occurs because each molecule within the sample gets polarized. The negative part, I'm making negative parts blue, are pulled up to be closer to this positive charge. And of course, it's electrically neutral, so at the same time, the positive charge must be moved down relative to the negative charge. So we end up with essentially a dipole. We have a little molecular dipole. It's still electrically neutral, but the positive and negative charges are separated now. So this is what the problem becomes. We have a piece of glass. We have a positive charge and a negative charge. The glass molecules will be polarized. The negative part will be on the top surface. The positive part will be on the bottom surface. And inside the glass, there will also be polarization. The negative part on the top end of the molecule, a positive part on the bottom end of the molecule. So you see, we no longer have a system consisting of two isolated charges. We now have a system with a semi-infinite number of charges. The number of molecules in a sample of glass is enormous because molecules are so tiny. So we'll have huge numbers of electric dipoles. Each electric dipole has an electric field, which has to be added. All these electric fields have to be added by the superposition principle. So the electric field for this system is very much affected by the glass, both at points inside the glass and at points outside the glass. Now, this looks like it's going to be a very difficult problem because we'll have so many of these electric dipoles contributing to the electric field. However, because the dipoles are so tiny, they can be treated as a continuum, and so we'll end up with a actually rather simple description of this system. It won't be exact because it won't take into account each dipole as a unit. We'll treat all of these dipoles as a kind of average effect of a continuum. And that will become something manageable. So the subject here is called electric polarization. The material, the matter, will be polarized. Now, if there are metals present, there can be even more of an effect because of currents. But what we'll be considering mainly is dielectrics, insulators, not metals. Materials that the atoms or molecules can be polarized, but they can't be pulled apart into separate positive and negative charges. Now, in addition to electric polarization, there's also magnetization. If there's a piece of matter present and some magnetic fields coming from some kind of external currents, well, that will affect the matter because the atoms or molecules that make up the matter will become magnetized. They'll develop magnetic dipole moments. Now, the topics of electric polarization and magnetization were covered earlier in the textbook, but we skipped over that because we were considering electric fields in empty space. Well, now we are going to have to take that into account. Let's start with the dielectric constant and the phenomenon of polarization. I described polarization on the previous slide. molecules within the sample of matter are separated into positive and negative parts. So we end up with a little dipole with maybe a positive side and a negative side. There's a dipole moment, and that contributes to the electric field. Now, we encountered dielectric properties briefly in the chapter on capacitors. If you remember, a capacitor is two separated conductors, but the gap between the conductors, the gap between the plates, could be filled with a dielectric material. The two plates have to be insulated from each other. They could just be separated by vacuum, but they could also be separated by some insulating material, like glass. That affects the capacitance. And if you think back to several weeks ago when we talked about capacitors, this was chapter 24. If the plates are separated by vacuum, you have a certain capacitance. Remember, the capacitance was epsilon 0 A, the area of the plates, divided by D, the distance between these plates. Well, but if you put between the plates some dielectric material, then the capacitance will change to C, which is kappa times the vacuum capacitance. There'll be this multiplication of the capacitance by a constant kappa, which is called the dielectric constant. Then the capacitance is kappa, epsilon 0 A over D. Now we're going to group together this pair of constants, and we're going to call that epsilon. So in Maxwell's field theory, the effect of the matter is to change the permittivity from epsilon 0, which is the permittivity of empty space, to kappa times epsilon 0. That's the permittivity in the material. And again, that's discussed in chapter 24. We did include this in some of the lon kappa problems. But if you don't remember that, you might go back and reread that section in chapter 24. It's equations 17 and 19 define the dielectric constant and the permittivity. For vacuum, or empty space, kappa is equal to 1. And the permittivity is equal to epsilon 0. But in the presence of matter, and I'm talking here about insulators, dielectrics, the permittivity is not epsilon 0, it's epsilon. So all of those equations that we wrote down earlier in the semester for electric fields, electric forces, etc., depending on epsilon 0, well, they really should have been written in terms of epsilon for a system in a dielectric. Now, epsilon is different for every material because unlike epsilon 0, which is a universal constant, epsilon depends on the material. The dielectric constant depends on the material. So for glass, there's a certain value of kappa. For water, there's a different value of kappa. For air, there's a value of kappa which is a little bit bigger than 1. Air and vacuum aren't that much different. So kappa is approximately equal to 1 for air. Well, we usually make that approximation. That's polarization, electric polarization. Now, there's also the effect of magnetic dipoles in the glass. From magnetization of the molecules, the permeability changes. Remember, the permeability of empty space is mu0, just a universal constant, 4 pi times 10 to the minus 7 in SI units. Depends on the value system of units. Well, in the presence of matter, that changes to mu, which is 1 plus chi magnetism times mu 0. Chi magnetism is called the susceptibility. And again, we can combine 1 plus chi to be kappa, but this is not kappa for polarization. It's kappa for magnetization. Now again, this was described earlier in the textbook in chapter 28. We didn't really talk about magnetic properties of materials earlier in the semester. And we'll be needing this, although it's usually not so important for problems with electromagnetic waves. So again, if you're interested in finding out more about this, read the section in 28 on magnetic materials. This is equation 23, relates the susceptibility to the, well, we don't call this a dielectric constant. There's only one kind of dielectricity. Kappa is always greater than 1. But there are two kinds of magnetic materials. There are materials where kappa m is greater than 1, usually only a little bit greater than 1. And theirs are called diamagnetic. But then there's a different class of materials where kappa is less than 1. Those are called paramagnetic. So in fact, there are different kinds of magnetism. There's diamagnetism, there's paramagnetism, and then there's ferromagnetism. But ferromagnets would not be included for electromagnetic waves going through ferromagnets. They're metals, they're different. But if you had some kind of insulator, it might have magnetic effects. Usually, the electric effect is much larger than the magnetic effect. So usually, we would just go ahead and set permeability equal to mu 0, same as vacuum. It would be a rare material where you had to take into account the permeability just for describing the properties of waves. Because the effect of the electric polarization is quite a bit larger. Something of the order of 100 times larger. So this will be our method of handling dielectrics. We'll replace permittivity of vacuum by permittivity of the material, which is the dielectric constant kappa times epsilon 0. And if we really want to be careful, we could also take into account magnetization, although that's normally a small effect. Let me say a little bit more about this technique where we replace epsilon 0 by epsilon. Let's go back to Maxwell's field theory and see how this comes about. We always have Maxwell's equation, the fundamental equation. Del dot E is rho over epsilon 0. That's Maxwell's version of Gauss's law, and that's universal. So that's something we would never change. Well, we could write it this way. We could say del dot epsilon naught E is rho. Divergence of epsilon 0 E is rho. Now, in vacuum, the charge density is just the free charges, the charge density of the three particles, or the free charges, unrelated to the sample of matter, just the charge density of the isolated charges. So then this equation becomes del dot epsilon 0 E is equal to rho free. This is the universal equation. This is the equation in vacuum or in free space. It's just the same where there's no charge except the free charge. But if matter is present, Then the charge density, as we saw previously, will have two parts. We'll have the charge density of the free charges, and we'll also have charge density inside the glass of the atomic or molecular dipoles. So then we have rho, the complete charge density, is rho free plus rho bound. Now it turns out this bound charge can be written as minus gradient of P, where the field P is called the polarization. So that's just a name. We can just name polarization and we can write a differential equation for the polarization in terms of the bound charge. The polarization is coming from the bound charge. And the polarization is caused by E. So, in fact, the polarization will be proportional to E in most materials. And we write the constant of proportionality as chi epsilon 0 E. Here's some constant of, here's some ratio. It's the ratio of the polarization over the electric field. So, it's P is proportional to E, the constant of proportionality is epsilon 0, which we always know that, times some material property chi. That defines a material property chi. Depends on the material. It'll be different for glass, it'll be different for water, it'll be different for any plastic material. Any insulator will have some material value of chi. Now let's go back and look at this fundamental equation. Del dot E is rho free over epsilon 0 plus rho bound over epsilon 0. I should have said rho free stands for the free charge density. Rho bound stands for the charge density coming from charge that belongs to the atoms or molecules in the sample of matter. All right, so on this side of the equation, I'll have rho free over epsilon 0, or actually I'll deal with this equation. I'll have rho free plus rho bound, and rho bound is minus del dot P. I'll move the del dot P over to the other side of the equation. So I'll have del dot epsilon naught E plus del dot P is rho free. So here's del dot epsilon naught E plus P, that's rho free. I no longer have rho bound, but I do have rho bound. It's here. It's in the polarization vector via this equation. Now P, I'm denoting that by epsilon naught chi E. So there's epsilon naught E plus epsilon naught chi E. Or I can factor out epsilon naught. It's del dot epsilon naught 1 plus chi E. Well, I'll group this together and call it epsilon. So it's del dot epsilon E. Epsilon is epsilon naught 1 plus chi. So I have this parameter chi, which is called susceptibility, and I have this other parameter epsilon, which is called permittivity. There's a lot of jargon in this subject. Well, okay. So then the equation becomes del dot epsilon E is rho free. That's the equation for the electric field, or rather the divergence, in matter. Del dot epsilon 0 E is rho free in vacuum. Del dot epsilon E is rho free in matter. So you see, all I really have to do to take into account the effect of the polarization is replace epsilon naught here by epsilon here. Now what's epsilon? It's epsilon 0, 1 plus chi. kappa is 1 plus chi. Kappa is the dielectric constant. That's 1 plus the susceptibility. Usually the susceptibility is a smallish number, so this is something not too far away from 1. Always chi is positive. The direction of the electric field, where do I have it? The direction of the electric field and the polarization field are lined up. If the electric field points northwest, the polarization points northwest. So that means chi has to be a positive number. So 1 plus chi has to be bigger than 1. So you see the dipole moment, the dielectric constant is always greater than 1. Or to put it another way, the permittivity is always greater than the permittivity of vacuum. Well, that sort of explains the electric case. I could go through a similar calculation for the magnetic case. We're mainly interested in waves. And for waves, it's really the dielectric properties that are most important. So we'll go on to now electromagnetic waves. Well, we studied the effect of, or the properties of electromagnetic waves in empty space last week. Now we're going to consider electromagnetic waves in a material. And this is especially relevant for dielectrics. Transparent materials such as glass or water or air. Materials that are transparent and made up of insulators. Metals, conductors, are quite different because they're not transparent. So waves don't go through a metal. Waves, you can't see through a piece, even a thin piece of aluminum foil. You can't see through it because light doesn't go through it. That's because the electric properties of a metal are quite a bit stronger because they can have currents. So we're considering the case of insulating and transparent materials. Maxwell understood the material effects as part of the field theory. We can just replace permittivity epsilon 0 by epsilon, which is the dielectric constant times epsilon 0. And if you really want to be accurate about it, you can replace the magnetic permeability mu 0 by permeability mu, which is the susceptibility times mu 0. I've said this several times already. Usually the magnetic effects are small for transparent materials. So, what are the field equations in the absence of free charge and free current? Remember, that's how we found electromagnetic waves last week. We looked at Maxwell's field theory with no charge and no current. We have del dot E is 0. Del dot B is 0. Del dot B is always equal to 0. Del dot E is rho free. Well, del dot epsilon E is rho free, but rho free is 0. So del dot E is 0. I really should say del dot epsilon E is 0. But if I assume that the material is uniform, that is to say there are no variations in the permittivity or the dielectric constant within the material, then that's just a constant. I can pull it out. So I have del dot E is 0. A del cross E is minus dB dt. That's Faraday's law, and that's always true. Matter or no matter, that's always true. Just like del dot B is 0, whether there's matter or no matter. And this is always true, whether there's matter present or not. But then we have Ampere's law. Del cross B in empty space, that's mu 0 epsilon 0 dE dt. There's no free current, but there can be displacement current. So this is, we normally would say this is mu 0 times the displacement current. And the displacement current in empty space is epsilon 0 dE dt. I better remember these are vectors. So E is a vector. J is a vector. Well, but I can just replace mu 0 by mu, and I can just replace epsilon 0 by epsilon. So then this becomes mu epsilon dE dt in matter. So these are the equations I have to solve. And they're exactly the same as the equations I solved last week, except I have a different constant here. Last week I had these equations with mu 0 epsilon 0. Otherwise the same. Well, so the same solution will work. So I'll look at the plane waves. I'll focus on the plane waves, harmonic in time, sinusoidal in space, traveling as a wave, and I just remember the formula from the formula for plane waves in vacuum. E is E0 sine kx minus omega t times j hat. And B is B0 sine kx minus omega t times k hat. So I'll have propagation in the x direction for this solution. Well, I could change that to any other direction, but let's just take the x direction. The electric field oscillating in the y direction. So there's the electric field oscillating in the y direction. Maybe I'll change the color for the magnetic field. The magnetic field oscillates in the z direction. So the magnetic field is oscillating in this direction, the third direction. So the electric field, the magnetic field, and the direction of motion, or the direction of propagation, the propagation direction is k hat. K hat is in the I hat direction. K hat is in the x direction. That's the direction of propagation. Better remember electric field's a vector. E, B, and K form an orthogonal triad. All right, so those are the plane waves. They satisfy these equations for mu 0 and epsilon 0. Well, the plane waves in a material are exactly the same, only we don't have mu 0 epsilon 0, we have mu epsilon. So remember when we were deriving the equations, we found a relationship between E0 and B0, actually two relationships. From this equation, K times E0 is omega times B0. Well, that's the same in matter because Faraday's law is universal. But this equation is K times B is omega times E, that's the time derivative, times mu epsilon. So using the same mathematics as last week, we have these solutions with these relationships among the parameters. And in particular, we can calculate the wave velocity. Remember, the wave velocity is omega over k. If I move the wave by one wavelength and by one period of oscillation, I would have k delta x minus omega delta t. And if those changes leave the phase unchanged, then k delta x minus omega delta t is 0. So delta x, the distance of translation in space, divided by delta t, the time interval, multiply both sides of the equation by multiply by omega, sorry, both sides of the equation, divide by k and divide by omega. Well, I'm really just solving these to be equal. So k divided by omega, so omega divided by k is delta x divided by dt. So pull the omega down here, pull the k down here. No, pull the dt down here. Pull the dt down here. I'll have dx over dt. Pull the k down here. I'll have omega over k. So that's the phase velocity, omega over k. Now, using these results, that is to be 1 over the square root of mu epsilon. Remember last week we had the phase velocity is 1 over the square root of mu 0 epsilon 0. Well, I have the same equations here, except instead of mu 0 epsilon 0, I have mu epsilon. So the solution for the phase velocity will be 1 over the square root of mu epsilon. All right, now I'm going to define what's called the index of refraction for the material, and it'll be denoted by n. The definition of the index of refraction of a material is the speed of light in vacuum, we always call that c, divided by the speed of light in the material. Okay? So these are the equations I want to remember for the next slide. V phase is 1 over the square root of mu epsilon. N is C over V phase. Okay, I hope you're taking notes, because these are all equations that you're going to need for the long kappa problems. We can relate N, remember that's an optical property, that's called the index of refraction, to the electric and magnetic properties of the material. For the electric property, I always use kappa. That's called the dielectric property. For the magnetic properties, I could use kappa m. That's the magnetic 1 plus susceptibility. That's the diamagnetic constant, or the paramagnetic constant for paramagnetic materials. We have this definition for the index of refraction. It's the speed of light in vacuum divided by the speed in the material. Speed in light in vacuum I know is 1 over the square root of mu 0 epsilon 0. And the speed of light in the material, I call that V phase, it's the phase velocity, it's 1 over the square root of mu epsilon, because it satisfies the same equations with just mu 0 epsilon 0 replaced by mu and epsilon. Or I can clean this up a little bit. It's the square root of mu epsilon over the square root of mu 0 epsilon 0. Now remember, epsilon over epsilon 0 is kappa. So I have here kappa, and mu over mu 0 was kappa for magnetism. So the index of refraction is the square root of kappa m kappa. So this optical property, having to do with the speed of light, is related to these electric and magnetic properties, relating to the polarization and magnetization of the particles in the material. Usually the magnetic effect is small, so we just approximate kappa by 1 for magnetism, and the main effect is from the dielectric constant. So n, for most materials, is just the square root of kappa. So it relates optics to electrical polarization. Light travels more slowly in a material than in vacuum. Recall, we had a minute ago, the dielectric constant is always greater than 1. The permittivity is always greater than the vacuum permittivity. That's because the susceptibility for electric polarization is greater than 0. So kappa is greater than 1. So n is greater than 1. So C is greater than V phase. or v phase, speed of light in the material, is less than speed of light in vacuum. V phase is c over n. It's less than c, n is greater than 1. Well, this leads to the optical phenomenon called reflection and refraction. Suppose we have light waves coming in and striking a surface where I have some index of refraction n1 above the surface and n2 below the surface. And the light waves are coming from the region with index of refraction n1, striking the surface. It's a plane surface, so you have to think of this in 3 dimensions. I'm just looking at a cross-sectional area. And it's hitting a surface of a dielectric with a dielectric constant n2. So, for example, this could be waves in air hitting the surface of a window. So it waves from air into glass. Or it could be sunlight hitting the surface of a lake. So I would have n1 equals 1, that's for air, n2 equals 1.33 for water. What happens is part of the light is reflected and part of the light is transmitted into the second material. So there'll be a certain amount of energy carried by this wave. Some fraction of the energy will be carried in the reflected wave, and the rest of the energy will be transmitted into the material. So here is the outgoing reflected wave. And here is the wave that's transmitted into the material. You know, we have light in, let's think of air and glass. So we have light coming in through air, hitting the surface. Some of the light will go into the glass, but not all of the light will go into the glass. Some of it will be reflected from the surface. Or it could be air and water. Have you ever looked at your reflection in the surface of a lake? You can see yourself if you look into the surface of a lake, because the light that's coming off of your face is reflecting from the water and going back into your eyes. So, in general, some fraction of the incident light, fraction in terms of energy, will go into the second material and the rest will be reflected. Now, the wave speeds of the incident and reflected waves are equal, because the wave speed for the incident wave is c divided by n1, and the wave speed for the reflected wave is c divided by n1. They're equal. So these two waves have equal speeds, and therefore the angles of the rays must be equal. We always measure angles of rays incident on a surface as the angle from the normal direction. So here's the normal direction. It's the direction perpendicular to the surface. So here's the surface. And again, you really should think of this as being two-dimensional, a surface, a plane. Well, okay. I'm just looking at it edge on, so it looks like a line, but in fact it's a surface. The perpendicular to that surface is called the normal direction. The incident wave is at an angle theta I, angle with respect to the normal. The reflected wave is at an angle theta r relative to the normal. And because these two waves are traveling at the same speed and they must be continuous at the surface, that means these two angles have to be equal. In other words, it's the same as a mirror. That's called the law of reflection. Theta r, r stands for reflected, theta r is equal to theta I. It's a mirror reflection. Mirrors behave in the same way. Of course, for a mirror, N2 would not be a dielectric. For a mirror, the lower material would be a metal. So suppose you have a mirror with a silver surface. Well, the electric field doesn't go into a metal. Metals are not transparent. Metals are opaque. So all of the energy would be reflected. But because the incident wave and the reflected wave are traveling at the same speed, that means they'd be reflected at equal angles. And that's their law of reflection, which can be used for dielectrics and can also be used for metals. That's reflection. Now we have, for a dielectric material, we have the light that goes into the material. And that is called the refracted wave. Reflected and refracted. It's at an angle of theta sub t. I'll call it theta sub t. T stands for transmitted into the material. I can't call it r because I already called r for the reflected wave. So there's theta r and there's theta t. I think in the book this is called theta reflected and this is called theta refracted. But it's a little simpler if you just give it two different symbols, theta r and theta t. You know, these are waves. So the wave fronts are big planar regions where the electric field oscillates in one direction and the magnetic field oscillates in the perpendicular direction. But to describe these angles, all I really need are what are called the rays. That is to say, the axis of propagation. So this is the incident direction of propagation. This is the reflected direction of propagation. This is the refracted direction of propagation. Now, direction of propagation is a big mouthful, so we call that the ray. Unlike the wave fronts, which are planes, the ray is just a vector. It's just a direction. Okay, so now what's the direction of the refracted wave or the transmitted wave? We have an incident wave at some angle theta I. There's a reflection, which is at an angle theta r, which is equal to theta I. And there's a wave transmitted into the transparent material with an angle theta t, t for transmission. Theta r has to be equal to theta I because the index of refraction is the same above the surface. But the index of refraction below the surface is different. And that means the speeds of the incident and refracted waves are not equal. This wave travels faster than this wave. You know, this wave is made out of wave fronts where the electric and magnetic fields reside. And those electromagnetic fields are propagating in this direction. And this wave is made out of wave fronts. Whoops, I didn't want to do that. And these wave fronts are traveling slower than the incident wave fronts. VI is C over N1. That's the wave speed in the upper region. VT is C over N2. That's the index of refraction, N2, in the lower region. These are different. Now, we can relate wavelength and velocity. The wavelength is the velocity divided by the period, or that's the velocity times the frequency. This wave has a certain frequency. This wave has the same frequency because the waves have to line up, have to be continuous at the surface, so they have to have the same frequency. So lambda I over lambda t is VI over VT because the frequency is the same. So that means that the wavelength of the transmitted wave is different from the wavelength for the incident waves, because the speeds are different, the wavelengths are different. Now they still have to be continuous on the surface. Oh, VI over VF, VI over VT, we see from this equation, it's N2 over N1. Now the projection onto the x-axis here, if we call this the x-axis, or the horizontal axis, let's say, the projection on this axis, the wave has to be continuous. So therefore, the wavelength projected down onto the horizontal axis, so divided by the cosine of the angle, but I measure the angle relative to the normal, so that's the cosine of 90 degrees minus the angle. That projection must be equal to lambda t, this wavelength, divided by cosine 90 minus theta t. Now, cosine 90 minus theta is the sine of theta. And this is the sine of theta t. So if I write theta I over theta t, well, sorry, lambda I over lambda t, it'll be sine theta I over sine theta t. And I know from here, lambda I over lambda t is N2 over N1. So sine theta I over sine theta t is N2 over N1. So that gives me what's called the law of refraction, also known as Snell's law. N1 sine theta I is equal to N2 sine theta t. Multiply this N1 up here, multiply N2 down, and multiply sine theta up here. You see N1 sine theta I is N2 sine theta t. That's the law of refraction, or that's Snell's law. And so that tells you what this angle will be. If you know what this angle is, and you know the indices of refraction, you can calculate from that the angle of the refracted wave. And there will be a whole lot of long kappa problems where you have to use Snell's law. All right, so the derivation of Snell's law is a little bit tricky. There's a little bit of geometry involved here. Actually, Snell's law can be derived in several different ways. It's derived in the textbook in a different way, a quite different way. In the textbook, the authors derive Snell's law using the principle of Fairmont. Fairmont was a French physicist and mathematician, and he had his own way of deriving Snell's law. And that's the method which is used in the textbook. But however you derive it, this is what you need to know. The law of refraction says n1 sine theta 1 is equal to n2 sine theta 2, where n1 is the incident region, n2 is the transmitted region. Theta 1 and theta 2 are the angles in the incident region and in the transmitted region. If n2 is larger than n1, for example, if I had waves coming from air into glass, then theta 2 will be less than theta 1. In other words, the direction of the ray is bent towards the normal when you're going from a less dense material into a more dense material. On the other hand, if I reversed all the arrows, I would consider waves going from the more dense material into the less dense material. I could have waves going from glass out into air. Well, the relation between these angles would still be given by Snell's law. And in particular, when light goes from glass into air, there's a critical angle where the direction of the transmitted wave goes to 90 degrees. So in other words, all of the energy would be reflected back into the glass. That's called total internal reflection. So total internal reflection is an example of Snell's law, where n1, the region of the incident wave, is actually greater than n2, where the refracted wave comes out at a larger angle. It's bent away from the normal. It's bent so that it doesn't actually go into the glass. It just goes parallel to the surface. And that's another topic that you'll find in the Law-Kappa problems, total internal reflection. It's just an example of Snell's law. But I'm not going to describe total internal reflection in the screencast. You'll have to either read it in the textbook or look it up on Google search. All right, so those are the principles. And now we go on to examples. And part 2 of the screencast will consider 2 examples, mirrors and lenses. Mirrors are governed by the law of reflection, the law of equal angles. Lenses are governed by the law of refraction, Snell's law. So we'll need these 2 principles of reflection and refraction in order to consider applications to optical instruments. And we'll consider both mirrors and lenses. So again, there will be problems on the Law-Kappa assignment requiring mirrors and lenses. So watch the second part of the screencast before you go on and try to do the later part of the Law-Kappa assignment.